Every accelerator chip built at an advanced process node passes through a room in Veldhoven, the Netherlands, where a laser fires at a falling tin droplet roughly 60 micrometers across. The plasma it creates emits light at 13.5 nanometers, and that light, the shortest wavelength used in any industrial manufacturing process on Earth, is the only thing capable of drawing the features on a modern chip. One room, one company, ASML. In 2023, the Dutch government revoked the export license that would have let that machine ship to China, and no extreme ultraviolet lithography system has crossed that border since. The question this map asks is not whether China can build a faster chip in the abstract. It is whether the supply web beneath any advanced chip still has a node China cannot route around, or whether a new line, running on photons instead of electrons, is already threading past the choke point before the gap becomes structural. A technology shift does not announce itself as a faster device. It rewrites the topology of the dependency web. A new line drawn through the graph that turns a dead-end node into a junction with a second exit. This map traces that web from a finished accelerator back through the nodes beneath it, reads each node's control status, and asks which junctions terminate in dead ends and which have quietly acquired a route out. The protagonist running through every segment is one wafer's worth of chemically amplified photoresist, a volume roughly equivalent to a small bottle of nail varnish, which we will follow from its synthesis facility in Japan through the exposure tool it coats, the pattern it receives, and the dye it was supposed to become. That wafer arrives at the fab already coated. Trace backward from the finished dye, a piece of silicon roughly the size of a fingernail, and the first thing you reach is the question of how its transistors were patterned at all. Transistor features at the most advanced process nodes are measured in single-digit nanometers. To print at those dimensions, the wavelength of light doing the printing has to be shorter than the features themselves, which means deep ultraviolet light. The previous generation, operating around 193 nanometers, runs into a physical ceiling. Below roughly 7 nanometers of equivalent feature size, the only industrial tool that works is extreme ultraviolet lithography. The machine generates extreme ultraviolet photons through a plasma discharge. A high-powered laser, built by Trumpf in Germany, strikes 50,000 tin droplets per second. Each droplet vaporizes into a plasma that radiates at 13.5 nanometers. Mirrors ground by Carl Zeiss to sub-nanometer tolerances, a polishing standard that itself required over a decade of interferometric measurement development, collect and focus those photons onto the wafer. ASML integrates this system across roughly 5,000 suppliers across Europe and the United States. No other company integrates it at all. This is not a market share claim that requires hedging. ASML itself states it, and no competitor disputes it. Chinese fabs, including SMIC, have confirmed they are operating without extreme ultraviolet tools, running older deep ultraviolet systems with multiple patterning passes layered on top of each other to approximate finer geometries. Think of a city where every road converges on one bridge, not because the planners designed it that way, but because the riverbed was only shallow enough to build in one place. Traffic can reroute over longer upstream crossings, but the load capacity is never the same. Multiple patterning is the upstream crossing. Each additional pass adds process steps, adds cost, adds yield loss, and still does not replicate the resolution ceiling of the machine it is substituting for. Node reached. Extreme ultraviolet lithography. Status: choke point. The line terminates here. No domestic Chinese extreme ultraviolet system has reached production readiness. No confirmed credible alternative process reaches equivalent resolution. ASML holds the only exit from this junction. The line does not start at the machine, though. Follow it one step farther back, and you reach the chemistry the machine depends on. The wafer our photoresist rides arrived at the exposure tool already coated. That resist is a chemically amplified polymer designed to react specifically at 13.5 nanometer wavelengths. The exposure triggers a cascade. Photons activate an acid generator in the resist. The acid catalyzes a deprotection reaction in exposed regions, and the pattern becomes developable. The exposed areas wash away or are retained, leaving behind the geometry the mask defined. The chemistry is extraordinarily specialized. The purity requirements are measured in parts per trillion for certain contaminants. The formulations that work at extreme ultraviolet wavelengths are overwhelmingly developed and manufactured in Japan, where JSR, Shin-Etsu Chemical, and Tokyo Oka Kogyo account for the substantial majority of advanced photoresist supply by most analyst estimates, though independent market share figures vary by segment and are difficult to verify with precision. The gases surrounding the wafer during exposure, ultra-pure hydrogen that purges the light path of oxygen and water vapor that would absorb extreme ultraviolet photons, noble gases used in adjacent process steps, come from a similarly concentrated supply network of industrial gas producers. Thinking of the resist as ink in a system where someone else owns the paper, the pen, and the printing press gets at the dependency correctly. The purity window for extreme ultraviolet resist is so narrow that the supply relationship operates like a single valve. One formulation, one tolerance specification, one point where contamination ends the print run. China has domestic photoresist research programs and multiple state-backed initiatives aimed at reducing import dependence. Reports suggest domestic suppliers are producing resist suitable for mature node processes, the older, less demanding geometries that have been in production for years. For extreme ultraviolet specific chemically amplified resists, the formulations that function at 13.5 nanometers, no Chinese supplier has publicly confirmed volume shipments to an advanced fab, and no independent benchmark of domestic extreme ultraviolet resist performance at leading-edge specifications has been published as of mid-2025. I think this is the node that receives the least analytical attention relative to how much the map depends on it. Most coverage anchors to the machine itself, the ASML system, the export control, the dramatic single object. The photoresist cluster is quieter, but its bypass status is arguably less resolved than the machine's, because the machine has at least generated a public accounting of what would be required to replicate it. The chemical cluster has not. The Zeiss mirror optics inside the exposure tool, polished to tolerances that no Chinese supplier has publicly matched, are a separate but adjacent node on the same line, also export-controlled, also without a confirmed domestic equivalent. Node reached: photoresist and process chemistry. Status: chokepoint. A second route is under construction, destination unconfirmed. Domestic Chinese alternatives are in trials for mature node applications. For extreme ultraviolet compatible formulations, reports suggest development is ongoing with no confirmed production volume at advanced specifications. Now trace the line one level farther back to the point before the resist ever sees the fab. The pattern the photoresist will hold has to be generated somewhere. An advanced chip contains billions of transistors placed, routed, timed, and verified against the physical rules of the manufacturing process it will be built on. The software that does this work is electronic design automation. A leading-edge design flow runs through tools that check for timing violations across billions of paths, simulate parasitic capacitance at interconnect layers, verify the physical layout against process design rules that can run to tens of thousands of individual constraints, and ultimately generate the mask data that tells the lithography tool what to expose. That flow is dominated by two United States companies, Synopsys and Cadence. A third, Siemens EDA, holds significant position in verification and simulation segments. United States export controls restrict the sale of advanced electronic design automation tools to Chinese chip design companies working on certain categories of design, and reports indicate the restrictions were tightened in recent years. The concentration is well documented by industry analysts across multiple years of coverage, though precise segment-by-segment figures vary. Chinese domestic electronic design automation has existed for years. Empyrean Technology and several other domestic companies have tools in active production. The critical qualification is scope. Reports suggest domestic tools handle analog design flows, certain digital flows, and mature node tapeouts. Here is where I have to walk back my own earlier framing. I had been reading domestic electronic design automation as a choke point with a bypass being actively built, which is correct in infrastructure terms. The road exists. But the gap between a road existing and that road reaching a specific destination is exactly the gap. The available evidence does not bridge. Whether domestic electronic design automation tools can close a leading-edge digital design at sub-7 nanometer process rules is not confirmed by any independent benchmark. No publicly verified tapeout at leading-edge specifications using only domestic tools has been reported. A map drawn with the wrong projection looks accurate until you try to navigate by it. Electronic design automation tools are the projection system for chip design. Every physical constraint of the process, how close two wires can run, how much current a via can carry, how diffraction bends around a corner at the lithography step, is encoded in the tool's models. A tool with incorrect or incomplete models produces a layout that looks right on screen and fails on silicon. The bypass road exists. Whether it currently reaches the destination is unverified. Node reached. Electronic design automation software. Status. Choke point. A second route is under construction. Destination unconfirmed. Domestic Chinese tools handle a documented range of design tasks. For leading-edge digital flows at advanced nodes, no independently confirmed tapeout demonstrates equivalent capability. Every node traced so far sits on the same line. Die to lithography, to chemistry, to design software. Each node is a prerequisite for the one before it. Now, a different kind of line enters the map. Not another step in that chain, but a route that bypasses the reason the chain was being pushed in the first place. The reason advanced logic has required smaller and smaller transistors is fundamentally a bandwidth problem. Moving data between compute elements fast enough to keep them fed, between memory and processor, between processing tiles within a chip package, between chips on a board, becomes the binding constraint on system performance as the transistors themselves get faster. The scaling wall means that at some point, shrinking the transistor further yields diminishing real-world performance returns per unit of engineering effort. Optical interconnect enters as a route around the wall itself, not around any node on the existing path. Replace the copper wires between chiplets, between dies, or between chips on a package with photons traveling through silicon waveguides. Higher bandwidth per unit of power, lower latency at distance, no electromagnetic interference to manage at the wire density that advanced packages require. If enough of the bandwidth problem can be solved through photonic integration, moving the data optically rather than electrically, the pressure to reach the most advanced lithography node relaxes. A chip that delivers competitive system throughput because it solves the interconnect problem does not need the same node geometry as one solving the bandwidth problem through transistor density alone. I want to be explicit that this is a hypothesis I am testing, not a settled read. Photonic interconnect is being narrated in some quarters, including by Chinese state media and by certain Western analysts, as a bypass around extreme ultraviolet lithography. That framing is too direct and too simple. Photonics does not bypass the lithography machine for making logic chips at advanced nodes. It bypasses the scaling wall that the lithography machine is being used to push through. Those are different nodes on the map. The question, the one the evidence does not yet answer, is whether routing around the scaling wall matters more, eventually, than routing around the machine. If the bridge is blocked, one answer is not to build a bypass to the bridge, but to ask whether the destinations can fit on the same side of the river. Photonic interconnect repositions the endpoints rather than bridging to them. The river, the lithography gap, remains. The rerouting is architecturally real. The question is whether the endpoints actually fit where the new route puts them. China's research output in silicon photonics and optical interconnect is substantial, publicly documented through academic publications and patent filings, and has been a visible state investment priority. Chinese institutions and companies are developing optical transceiver components and silicon photonics integration platforms at prototype scale. Reports suggest multiple programs are at prototype stage. No confirmed production deployment of photonic interconnect as a substitute for advanced node scaling has been independently verified by any manufacturer, Chinese or Western. Node reached, photonic interconnect as a scaling bypass. Status: junction under construction. China has traced a credible research line through this node, but the line's far end, production volume integration into competitive accelerator packages, remains unconfirmed. This is a new route on the map, not yet a working road. Pull back now to the node where the line genuinely stops. Not every choke point on this map is permanent. Some have bypasses under construction, some have working domestic routes for older process generations, and the photonic line introduces a different geometry altogether. But the extreme ultraviolet light source itself, the tin droplet plasma mechanism, and the Zeiss mirror system trained on it, is the node where the map runs out of exits, and the exit under construction is the least confirmed. An extreme ultraviolet lithography system is not a single invention that can be replicated by studying one example. It is the convergence of roughly 3 decades of coordinated development across laser physics, plasma physics, precision optics, and vacuum engineering, instantiated in a supply chain of several thousand components that each required years of independent qualification. The service relationship matters as much as the hardware. A Chinese fab running an extreme ultraviolet tool without ASML maintenance access would face a system degrading over time with no credible domestic pathway to replace the components that wear. Export controls restrict not just the machine, but the service contracts and the replacement parts. No Chinese institution has publicly demonstrated a plasma-based extreme ultraviolet source operating at the power levels required for production throughput. The strongest case for an eventual bypass is not a domestic clone of the existing machine, but a physically different approach: free electron lasers or alternative plasma configurations that produces usable extreme ultraviolet photons through a different mechanism. Chinese state research programs in high-energy photon sources exist, though they are not primarily aimed at chip lithography, and the physics overlap is real. A longer horizon argument: if photonic interconnect and chiplet architectures reduce the performance penalty of staying at mature nodes significantly enough, the production need for extreme ultraviolet at leading-edge geometries diminishes, making this choke point less decisive even if it remains impassable, because the traffic that needed it found a different destination. Both cases are real. Neither is close to resolving. The dead end sits at the junction where the tin droplet meets the laser. The plasma emits its photons, and the mirrors focus them onto a surface they cannot reach from China. The map around it is changing, but a changing map is not the same as an open road. Read the full map now. Some nodes have acquired working domestic routes. Mature node fabrication tools from domestic producers, including Nora, are in active production for older process geometries. Certain memory tiers have seen domestically produced alternatives confirmed in independent reporting. Process chemistry for non-leading edge applications has established domestic supply. Those are junctions with working lines through. The remaining cluster of choke points is different in kind. Extreme ultraviolet lithography has no confirmed domestic system at production readiness. Extreme ultraviolet compatible photoresist has no confirmed domestic volume at leading-edge specifications. Leading-edge digital electronic design automation has no independently verified tape-out at advanced nodes. Photonic interconnect has a confirmed research line, but no confirmed production integration. My read of this web is that it does not close into self-sufficiency on the timeline most coverage implies, not because any single choke point is permanently impassable in principle, but because the choke points cluster on the same line. Extreme ultraviolet resist, and advanced electronic design automation are not three separate problems requiring three separate solutions. They are three consecutive nodes on a single line, and that line has to work end-to-end before a competitive leading-edge die can come out. Routing around all three simultaneously, while also bringing photonic interconnect to production scale, is a coordination problem of a categorically different order than solving any node by itself. The photonic bypass is the most interesting line on the map, precisely because it is the only route that does not need to pass through all three. But its far end is the least proven of any route this map has traced. The wafer's worth of photoresist that opened this map is still waiting at the node where it arrived, coated, queued, and dependent on a machine it cannot reach, and a light source no domestic supplier has lit at production scale. The web is being redrawn, line by line. But a map under construction is not yet a map you can navigate. Which node do you think closes first? Electronic design automation software at leading-edge specifications, or photonic interconnect at production volume? And what would that change about the shape of this web? Put your red in the comments. I'll respond to the arguments that push back hardest on mine. If you want to follow the next line as it gets traced, subscribe and turn on notifications. The next map starts where this one leaves the choke points open.